So hello friends, welcome to my channel. Let's see the continuation. uh, Here let's see what is the dynamic range and the source of noise and sources of noise. Now actually in a micro components, those all components are will be linear. That means when some output is directly proportional to input. For example, let us give an input of 5 dB and it has a gain of 2, then it will be 10, like it is like a y is equal to mx. So y is equal to mx, it is a linear, right? So it should be like that, but practically it won't be like that. What happens up to in certain range only it will be linear. So that linear portion we call it as a dynamic range. So what happens, uh, what is below that linear and what is above the linear, we'll see. So the below that linear we call it as a noise. So we can see here, this is a this part. Okay, this part is called region 1. That region is called noise. Generally we call it as noise. Basically this entire thing is called noise floor. Basically this determines whether the signal is fit for like taking or not. Like for example, the values of that signal is very less, way less than this. See this noise floor, then we consider that as a noise only. Okay, and then as for at certain point we are able to, at certain point of input power, we are able to see the linear curve, linear graph. So until 0 to this point we call it as what you call noise, n naught. Basically we call this height as n naught. Okay, we call that as n naught. Now coming to the higher this region. Okay, in this region we can see there is a this curve is deviating from the actual path, that is this, right? Actually it should go like this, but it is deviating and going like this. So at where at which point it is getting deviated is, we'll call it as a compression point. Basically we call it as 1 dB compression point. So why it is called 1 dB compression point? Because as we can see, uh, when the input, for example, let us take an input as 5 dB. Okay, let us take an input as 5 dB, but what happens, we are getting a output of 4 dB. Okay, we are getting an output of 4 dB. That means the difference between the input and the output is 1 dB less, right? So so we call that point as 1 dB compression point. Wait, I'll show the definition. So the 1 dB compression indicates that for a given input, the power level of the output is 1 dB less than the desired power. That means actually what happens, for example, if I give an input of 2 dB and I am getting I has to get a dB of 10 dB. Okay, I has to get 10 dB. But what happened? What is happening? I got only 9 dB as a output. Okay, that means for a gain of 5 has to get 10 dB, but I am getting 9 dB. That means there is an actually there is a difference of 1 dB, right? So that point we call it as 1 dB compression point. Now coming to the amplifiers, there will be two. We'll have amplifiers in two different sections. One is at the transmitter side, one is at the receiver side. So why do we need? I think it's already covered, right? Yeah, it's all cover. So when you kept a power amplifier at the transmitter, we call it as power level power amplifier. When you kept this amplifier at the receiver side, we call it as low power amplifier. I already told why it is called low power amplifier. Sorry, low noise amplifier. And also I told what why is it called low noise amplifier in the previous video. And so now coming to this, so we defined this range and also this minimum range. So what is this linear range? This linear range is called dynamic range. So this dynamic range is a formula, that is the maximum point at which it can handle, because after that the 1 dB compression it is deviating, that means it is not able to handle the linearity. So that is the highest point, that we call it as some PA, P naught. Okay, that is P naught. What is the minimum point where see this up to this point it is noise only, no? So this point is called N naught. So basically P naught by N naught, we call it as dynamic range. So that's what we call highest signal level of the amplifier can handle by the lowest signal level this amplifier can handle. So that is the dynamic range. So units of a signal range is in its terms of watts. Basically, it will be in watts. So noise floor, it is the noise level below which signals cannot be detected under the same measured conditions. Next, 1 dB compression also we defined. So generally an amplifier will be having output P naught power, which is like gain multiplied with input power. So above expression only holds for the but actually it should hold for all P for all values of input power it should hold, but in practice it will not be the case. So it is because noise generated by the amplifier itself, some non-zero itself, because there will be some noise that will be generated by the amplifier itself. That's why even if you give an input 0 watts, you will get some output as some value, because you can say that input is 0, gain is 0 into 0, you have to get 0, no? Gain into 0 means 0 you have to get, but we are getting some positive or some value, some we are getting some power value. Why? Because the noise is negative nature, that's why even that value is 0, 0 plus some noise, so we are getting the noise value like that. So noise power and the equivalent noise temperature. Let's see how the noise will be. So even I will take a resistor at some temperature T. I don't even give the source to the resistor, just voltage to it. But even still, it will generate some voltage. That is the noise voltage basically. So when you connect a resistor to a DSO, we'll see some waveform. Even when you don't have any source, so that waveform is basically due to noise. Okay. So according to the Planck's blackbody radiation law, we can know that the voltage for a particular temperature and frequency, we can know the what is the voltage we'll get. So Vn is equals to, or the noise voltage is equals to root over 4 hfbr by e power hf by kt minus 1. This minus 1 is not in the exponential, it is in down below. So what happens here, h is Planck's constant, that is 6.6 into 10 power minus 34 joule second, and f is the frequency, b is the bandwidth, r is the resistance, h already know, f you know, k is the Boltzmann constant, that is 1.3 into 10 power minus 23 joules per Kelvin, and T is also temperature in Kelvin. Remember, in this you will substitute all, anywhere you get T, you will substitute in Kelvin only. Remember that, not in degrees. Okay, so okay, we know this. So if for example, if hf by kt is much lesser than 1, okay, because as the frequency is more, and the Planck's constant is also like 10 power minus 34, we got some value, and okay, let us take an example. Let's see and see. So let f is equal to 100 gigahertz and T is 100 kilo ohms, sorry 100 Kelvin, then hf value is like 6.6 into 10 power minus 23, and kt is like 1.4 into 10 power minus 21. So when we compare this, this value is much lesser than 1. So sorry, okay, this ratio is much lesser than 1. So what happens, due to by using the Taylor series expansion, when this e power x, where x is much lesser than 1, we can simplify the expression of e power x minus 1 as x. That means e power hf by kt minus 1 is approximated to hf by kt. So this denominator is changed to this value. Now what happens, the hf and hf gets cancelled, and this kt will go to the numerator, and we got Vn is equals to root over 4 kt br. So only when you have to use this Vn and when you have to use this Vn. So if the ratio of kt by hf by kt is much lesser than 1, we'll use this ratio. Otherwise, if it is greater than 1, then we'll use this formula. And coming to when we try to generalize this in a circuit, this formula in a circuit way, or equivalent circuit way, the circuit will be looking like this, with a resistor R having some input voltage Vn, that is this Vn, and this is connected to an ideal band pass filter having B, that is this B, okay, is connected to some load. So basically this is the equivalent circuit for a noise resistor. So connecting a load resistor R results in maximum power transfer from the noisy resistor. with the results that power delivered to the load in a bandwidth B is. So basically now we are calculating, previously we calculated voltage, now let us calculate the power. So noise power is basically the noise power, the formula is finalized to Vn square by 4R. Okay, so Vn square by 4R. We know what is Vn. Above the equation root over 4 kTBR. So square, no, root and square will cancel, and that 4 and 4 and R get cancelled, and we left with kTB. So from this we can finalize that noise power is equivalent to kTB. Okay, this important result gives the maximum available noise power for the noise resistor at temperature T. For in this example, in this expression, if the B value, that is bandwidth, is tending to 0, the noise power also will tend to 0, obviously directly proportional, and same as for T also. If T greater than 0, the noise power will also be tends to 0. So that means what can you say, as we have a less smaller bandwidth, we'll get less noise power, and also if we have a cooler device, we'll get less noise power. But let us take the opposite scenario, that is if bandwidth is increasing to infinity, or if we have a infinite bandwidth, then we'll get power also infinite. This is called ultraviolet catastrophe, which does like this does not occur in reality. If an arbitrary source of noise, basically we call it as white, because as you can see that this expression is independent of frequency. This noise power is independent of frequency. That means for all values of frequency it will be constant. That's why you call it as white noise. Okay. Okay. Now equivalent noise temperature. So what is an equivalent noise temperature? So equivalent to noise temperature is basically the temperature at which the same amount of noise is being produced by a source. Like let's say this. Let's take this. Let's take some source that is named as arbitrary white noise source. That means this source will generate some noise. This is some device. I want to represent this device in form of a resistor having some temperature. Okay, this basically these two are equivalent representations. In this, we represent this device as a resistor and has some temperature. So as this resistor is a constant, so fixed value, we want to know the temperature. How much temperature applied to this resistor, we will get the same amount of noise that is occurred here. Okay, while increasing from some value of t, we are increasing, and for at a particular value of t, this and not and this and not got matched. Okay, so that temperature is called effective noise temperature. Okay, basically we call this as an, actually you can also take as an input one, or the effective noise temperature is for the device itself. Like device in the sense an amplifier, like that, some, or a amplifier or a band pass filter, some for that particular device. So where a noise power device. Okay, so from this what we can write, as we already know that n is equals to kTB, right? Basically we know that P is equals to kTB, but basically N, P and all same. N is also power, P is also power. Okay, it depends, like notation, like if it is N naught or Pn, both are represents the noise power only. Okay, N naught is also noise power, Pn is also noise power. Just the naming is different. That's it. So basically, N naught is the output noise power. You can name it all that like that, in that way. For example, if it is Ni, then it is input noise power, like that. Okay. So the output noise power that is resulting is kTB. So the T is what you call it as here T, right? Effective noise temperature. That's why N naught is equals to T into Kb. So from that effective temperature, how can we write T is equals to N naught by Kb? That's what we wrote here. For equivalent temperature T, there will be a fixed bandwidth B for a noise source. So here from this expression, for a particular value of bandwidth, we will get one particular value of T. That's what he is saying. Now let us have some discussion where there is some amplifier which has a gain G. I want to represent that scenario in two different ways. Either what, but I need the same outcome. That means the outcome should be G into KTEB. Okay, that means actually KTEB, that is as we seen here, N naught is equals to K TEB. Okay, I think I can't write here. You got my point, right? N naught is equals to TEB. Okay, TEKB, where TEKB, where this is passed to an amplifier with a gain G. That's what we want this as an output. So this output can be expressed in two ways. Either we can take a noisy amplifier with an ideal source, or with a noisy source with an ideal amplifier, or a noiseless amplifier. In the both scenarios you will get the same, that is depicted in these two circles. See here, I am taking noisy amplifier and I am giving an ideal source. That means which has ideal source, that means we'll get ideal source only if it is at a 0 Kelvin only, because there will be no temperature, right? 0 Kelvin is an absolute temperature that we can't reach, that's why it is called ideal also. Okay, 0 Kelvin we can't reach. So basically there in that point there will be no thermal noise, so that's why the input noise power is also 0. But as it is said, it is a noisy amplifier, so this amplifier itself will generate some noise. So basically these two are in cascaded only, no? This will be added to this and the resultant will be getting this here. So basically how can we write the output? Total effective output can be written as noise power by resistor plus noise power by amplifier, total term multiplied with the gain. Okay, this is how it will happen. So noise input by receiver resistor, that is Ni. So Ni into Z plus TEKBG, because the noise power by amplifier, what you know, that is the device. For the device I told you that TEKB, that has an amplifier of gain G, right? So that's why G into multiplied. So the entire here we see that Ni is 0, that's why this term will be 0. We are left with TEKBG. And the other scenario, basically it is noiseless amplifier. So in the other scenario, what we can write? In this scenario, this amplifier is ideal, basically. So the entire thing we need to get GKTEB, right? So what is the value of TE from here? N naught by GKTB. That's what we wrote here in the reverse way. That's it. This is ideal, but this resistor has some noise. This resistor has some temperature that is equal to N naught by GK. That's what. Okay. From that also we'll get the same expression. Now measurement of noise temperature. So this noise temperature will be found out by using Y factor method. So this how it works. So this in this what we'll take. Okay. Basically we'll have two resistors. One is at hot temperature, one is at cold temperature. The hot temperature is at so basically this always in this RF we'll take T1 as the higher temperature, T2 as lower temperature, that is always T1 is greater than T2. Okay, and the difference should be very high, huge. For an example, if the temperature is of the hot temperature will be at some kilo Kelvin, suppose 200 kilo Kelvin or 100 kilo Kelvin, like that, but the colder temperature will be like 77 Kelvin. See how much difference. So that much range should be at least. So now there will be some switch where we can connect either to, first we can connect to hot, after that we can connect to cold, like that, and that wire will be connected to a gain amplifier. We'll see the outputs. So here what will happen, first when it comes to T1, when we connect to T1, this is also some noise is there, no, because it has some temperature, so it will generate noise. And also this amplifier also we are seeing that it is a noise. That means T effective temperature is there and gain bandwidth is there. So these two are basically practical things. So what happens, they will be added up. So noise generated by this resistor will be T1 KB into Z, because what in the previous how happens, this noise plus this noise entirely multiplied with G, or others I will go with this fashion only. What is an input by the resistor? T1 KB. What is the noise by this? TE KB, right? KB plus TE KB. So this entire thing is multiplied with G, right? Is multiplied with G. that's what we'll take. So that's why we'll get an expression of this for n1, that is for t1 we'll get n1, for t2 we'll get n2, the same way we'll get n2. So the ratio between n1 and n2 is y is equals to n1 by n2. When it as g, k, b are common, we'll cancel out and we'll left with t1 plus te by t2 plus t greater than 1, because as t1 will be higher than t2 and obviously this ratio will be greater than 1. So when you rearrange this, we'll get te as t1 minus y t2 by y minus 1. We'll get this ratio. Okay. So to have the accurate results, we'll take this should not be t1 and t2 should not be close, as I told previously. There is another way also doing. In practically, how they will do is they will take one temperature as T0, one resistor as at T0. T0 is the room temperature, 290 Kelvin, and the other temperature can be either hot or cold. If you take the other resistor is at hotter temperature, we'll get Te as T is greater than T0. Okay. If you take T the other temperature colder than the room temperature, then we'll got T is less than T0. Okay. So this is what. So but basically this for this normal devices, when it comes to like an active source. Okay, if the device is an active, the input is like normal resistor, no? If that resistor is not a, like if it is not a resistor, if it is some active source, an active which can also generate energy, there we can see what happens. The value basically when it is an active source, it definitely internally it will generate some temperature. So what happens when you take that same device at the n0, that is at room temperature, the values are n0 and n0. For example, it is an n0. Okay, but what happens due to the temperature internally, due to the temperature generated internally, it is we just denote it as Ng. Okay, so basically this Ng will be greater than n0. Okay, Ng will be greater than n0 because temperature is increased. That means how much it is deviated from the temperature, room temperature. Okay, when the device, how much it is deviated when the device is at room temperature, we call it as excess noise ratio. So basically excess noise ratio in dB will formulate as 10 log Ng minus n0 by n0. Okay, we can also write in terms of, this is in terms of power, the same thing you can write in terms of temperature, that is 10 log Tg minus T0 by T0. So that's what Ng and Tg are the noise power equivalent noise at a and equal noise temperature of a generator, and the n0 and T0 are the noise power at the room temperature. So basically in the further video we can see that Ng and Tg will be changed to like P0 or T, like that. I will show you here. Can also be written as Pn and Tn. The both are same. That is like a generalized statement we wrote. But when it comes to our discussion, we just replace the terms as Pn and Tn. Okay, the meaning doesn't change. So the Pn and Tn represent the noise power and the equivalent noise temperature of the active noise generator. P0, T0 are same, equal noise temperature of passive source at room temperature. The same. The noise figure. So basically the problem is the direct one. They have given n1 and n2. So we need to convert into normal values. Here first it is in dBm. So if it is millidecimals, so it is minus 62 dBm. If you want to convert this dBm into dB, we should subtract it by minus 30. So minus 92. We know that how to convert dB to watts. That is 10 log x. Okay, 10 log x is equals to minus 92. So find out what is it, like that. So the same way you'll get to here, and as its whole input and also connected to an amplifier where the input has temperature they have given. So from that we know that GK TSB, and output also that noise for this amplifier, that GK TEB, add both, we will get N0. So this is same. So that's why for an active noises, the Y factor method is not that appreciated method. So that's why you'll go for ENR. So instead of using a resistor at higher temperature, they will use active noises which will be at very high temperature compared with room temperature. That means the active noise source only. What is the use of active noise source is in Y factor method. General what we are using a resistor at high temperature, right? They may use the active noise source instead of that, which will be very high temperature compared to the room temperature. So instead of maintaining at the temperature, we just directly give an input as an active noise source. That's it. So now coming to the noise floor. So what is a noise floor? Noise floor is the ratio between input SNR by output SNR. That is the noise figure. So it will be greater than 1 only, always. Okay, greater than or equals to 1. So from this we know already what is Ni and N0. Ni is input, that is some KTB. That means some take T0B. If it is at room temperature, KT0B, and the noise will be what? N0 will be what? KT0B plus TEB, right? If it has some gain also, you will multiply with gain. Entire thing will be multiplied with gain. So when you substitute and rearrange, we will get the formula as this: F is equals to TE plus T0 plus TE by T0, where we rearrange and we got 1 plus TE by T0 greater than 1, and we want it, if we wanted this in dB, 10 log of this value, that's will be greater than or equal to 0 dB. There is a special case where this T0 is equals to 0. For an basically when it happens for a noiseless network, the T0 will be T is equal to 0. So from this expression you can see this term will be 0, that so this term will be 0, then F is equal to 1. When you find the log of 1, that is 0. So in dB it is 0 dB, normally it is really 1. So from this expression we can also write what is T. T is equals to T0 into F minus 1. Okay. So these are the numerical where we can see they have given Y, so they have given that cold load as 77 Kelvin. So they also measure the Y value, Y factor ratio they have given, and also what is the ENR value they have given. From the ENR we will find T1. Okay, T1 means hot temperature. T1 minus T0 by T0, right? Because active source will be at higher temperature than T0, right? That's why that from that statement we directly took this as T1. The T so we got the T1 value, Y factor we know, we can get TE also. From the TE you get F, right? That's how we can do the same thing this for the other problem also. So basically this is M1. Now coming to the other model, which is called where we'll find that dynamic range. How to find dynamic range? I told you in the first starting that at the beginning I told you that this level is N0 and this is P0. To find N0, what is the formula? K into G TEB. That means that what is the basically what is the noise that is generated by the device. Okay. P out is for a particular input we'll multiply the gain, we'll get Pi into G is P0, right? So we'll get P0. From that so here we will find what is P0, as they have given that what is the gain and also what is the input power they have given. So we can find what is P0. So P0 we wrote it in dB, or we can write in any way. If you wrote in normal values, we will divide P0 by N0. If you want to use the same dB values, we'll subtract them, because ratio, no, we'll separate the dB values. Anyways, it is fine. So N0, how to find N0? We know that kg TEB. They have given TE gain, they have given bandwidth, and also we know K. From that we will find N0. So in the next video we will see what is the noise figure of a lossy two-port network, and how to solve the problems when they are given in cascade form.